Hi everyone, welcome back to my channel. Today we're diving into a super important topic that every programmer should understand: concurrency versus parallelism. We'll be talking about these concepts a lot in future videos, so it's crucial to get a clear grasp of them now. To make things more exciting, I've got a fun and easy to understand example lined up. And if you stick around until the end, I will share some practical tips and examples on how to work with concurrency and parallelism Go. So let's think about cooking a meal. Imagine you are making a three-course dinner: a salad, a main dish, and a dessert. If you are making your meal concurrently, it's like prepping the ingredients for all three courses at the same time. You chop vegetables for the salad, then while they marinate, you start boiling water for pasta. As the water heats up, you mix ingredients for the dessert. You're not finishing each dish one by one, but rather working on parts of each dish. You're managing multiple tasks by switching between them, and this is essentially multitasking, right? But on the other hand, when you're talking about parallelism, it's like having three friends in a kitchen. Each one is dedicated to make one course. One friend makes the salad, another one cooks the main dish, and the third prepares the dessert. However, concurrency is more than just multitasking. It's about structuring your workflow to handle tasks efficiently. Think of the entire dinner preparation as, as being a single process, with each task: chopping vegetables, boiling water, and mixing dessert, acting as a separate thread within this single process. These threads run independently but need to be coordinated to ensure everything is ready on time. For example, while mixing the dessert ingredients, you need to keep an eye on the boiling water to prevent it from boiling over. This coordination is the essence of multi-threading, managing multiple independent tasks concurrently inside a single process, right? And to optimize your workflow, you can ensure a seamless cooking process this way, right? So when you are doing your dinner alone, it's like that you are the processor, right? You're processing everything alone. And each course of your meal is a thread. In our example, we have three threads, which are essentially three tasks, right? And this is the dinner making process, which is the combination of the three threads, right? Which is essentially one process. So please notice that not all concurrent programs will be executed on a single process. In programming, concurrency is about structuring your code so it can handle multiple operations at once, like you multitasking in the kitchen. It's about managing multiple tasks that make progress without necessarily finishing them at the same time. So you won't necessarily finishing them at the same time. Parallelism, on the other hand, is about executing multiple operations at the same time. It's similar to your friends each cooking a different part of the meal simultaneously. So when you're doing that with your friends, it's like having three processors, right? Or three cores. And now you are doing three processing at the same time. You still have three threads or tasks to be done, and you still have the dinner making process, right? And this process have all the three threads or the three tasks. Please notice, not all parallel programs will be executed on a single process. But to ensure all tasks are completed efficiently and in sync, we need a way for these tasks to communicate their progress and a method to wait for all of them to finish. In Go, the most commonly used tool for this purpose are channels and wait groups. So they are the most used ones, right? So you have your process, and you have all the tasks or threads inside this process, right? And you need a way to communicate when the tasks is done, so you can assemble all your dinner, right? So most of the times you will use channels and wait groups, and then you can finish your job and do whatever that's needed. So channels allow different tasks or quote threads to communicate with each other, making sure that each part of our dinner is prepared in the right order. Meanwhile, wait groups provide a mechanism to wait until all these tasks are done, ensuring everything is ready at the same time. Take a look on the following GIF from Level Up Coding. So here you can see how concurrency is working, right? This would be like our CPU, our core. And on concurrency, the tasks are being switched, right? We're switching between multiple tasks. And on parallelism, they're all being processed at the same time, right? So when you see a GIF like that, you can visually understand much better. When you write a concurrent program, your code may or may not be executed in parallel. The reality is that it's gonna depend on the machine that it's being executed, right? So you write concurrent code, but it doesn't mean it's gonna be executed in parallel. If the machine have only one CPU or one core, it's gonna be concurrent, right? And if it have more than one CPU, it's gonna be executed in parallel. But let's think for a minute. We can improve our system even more. Imagine if instead of you alone multitasking, you assign specific tasks to different threads. One thread is responsible for chopping vegetables, another for boiling water, and another for mixing the dessert. These threads need to communicate and coordinate to ensure that the meal is ready simultaneously. For example, the vegetable chopping thread should notify the salad mixing thread once it's done, so the salad can be assembled while the pasta is cooking, right? So we can improve much better our system. Or yeah, you basically can spawn more threads, and or in our case, just call a new friend. And of course we still need a mechanism to wait for this task to be finished so we can finish our job. Let's now understand how each of these tools would look like in Go. The tasks or threads would be the Go routines, which are essentially lightweight threads. The process would be the currently running program. The communication would most likely be channels. In the most of the times it would be channels. Let's see how this would look like in Go. So here we have the functions, which is chop vegetables, boil water, mix dessert, and the final one, prepare dinner. I know this is too simple, but yeah, here we are simulating some work. Just we are just waiting something just for simulation purposes, right? And right here I have the current time, and we will print how much time it took to finish this work, right? So in our main func, we'll also have the now variable, so we can see in how much time it have finished our work. And here's the wait group. We'll use that for to wait. And right on this line, we are adding 3 tasks to the wait. So to the wait group. So it's gonna wait for 3 tasks. Right here, we have a go routine, which is a lightweight thread. And here we are basically spawning a new thread. And when this function finish, we'll mark this task as done, right? And we are doing the same time with the boil water, and we are doing the same time with mixed dessert. Right here on this line, this is very important because this is the waiting mechanism. We're waiting for all tasks to be done. When all tasks be done, we'll go to this line, and it will print in how much time it took to make all parts of our dinner Then it will prepare our dinner, which will take more 500 milliseconds, right? And it will print for us in how much time it took to make the whole meal, the whole dinner. So let's run this code and see. Let's see what happens. So yeah, as you can see, the boiled water took 200 milliseconds. The mixing dozer took 300, and chopped vegetables 400. Right? All those tasks were done in 400 milliseconds. Right? And we are printing that right here. As you can see, it waited, and it waited for the longest task to finish, right? So we have done everything simultaneously, right? And then it prepared our dinner, and our dinner took more 500 milliseconds, right? So as you can see right here, the whole dinner took 900 ms. But there's a problem. The previous code isn't really using any communication mechanism. We are just printing messages in the console. Let's modify our code so we can use channels to communicate. There are plenty of ways to do that in Golang. So I will just return a string from each function and an error. The following examples, they're just simulating real world tasks. And in a real world scenario, you would have to handle errors properly, especially in Go, which is a language that you are encouraged to handle errors like all the time, right? So let's see how our functions are right now, right? Right here, I have put it some comments so you can see what's happening. We still getting the time that when this function call starts, right? We are simulating some work right here, and this is the string that we are gonna return, right? In a real world scenario, you'll probably have an error inside here because you'll be doing some tasks and so on, and you would return it somewhere in your code if any errors exist, right? The other functions are basically the same thing. And I haven't done anything with that, right? So they have the same, this basically the same structure. So let's see how we are calling them right now. We still have the start, so we can correctly see when our main function starts and when our tasks finishes, right? Right here, we're making a channel of strings, and this buffer channel will have a maximum capacity of three string channels, and this is our error channel, which we only need one because if any errors happens, we just want it to close our program or do whatever, handle the error, right? We don't want to finish the task on this case, right? Right here, we are spawning our Goroutines, but there are some the key differences right here. The first one is we are getting our string, which is returning from chopped vegetables, and the error. And if any error happens, we are gonna populate our error channel with this error, right? If no error happens, we'll send our string to our done channel. We'll buffer our buffer channel. Okay. We'll be doing the same thing right here and the same thing here. Right now, we are calling the wait group, and we are closing our done channel because we need to close it. inside a thread, right? Not a thread, a goroutine, right? And we will make a loop. Inside this loop will iterate until 3, right? Because our buffer channel have only 3. And inside this loop, we have a select statement, right? You don't need a select statement. You could have looped from for inside or your buffered channel, your buffered done channel, and you could have done a new loop inside your error channel and return it, whatever. But this is a much more better approach, right? Right. Now let's see what happens when we execute this code. As you can see, we got the same output, but you may ask me now, why am I gonna do that if I have to write much more code and so on? And there are plenty of reasons to do that. The number one reason is by returning the content instead of just printing it, we could have used it anywhere else, like returning in JSON from our API or sending to another service or gRPC, whatever you can use for whatever you want, storing the database, and so on. The number two reason is by checking and returning errors, we can correctly handle them, which will make our life much easier when debugging and also make our code base much more robust and reliable and with much less bugs, right? The number three reason is we could have used loops on each of the channels created so we can return it and handle each of them. But using the select statement will allow us to not only have a more idiomatic code, but especially to handle both completion signals and errors at the same time, right? So using the select statement will help us to have a more performant and easier to understand code. When an error occurs, it will be returned immediately. So we don't have to wait for all other Go routines to be finished. And that's amazing. This is a powerful feature from Golang, right? When you use the select statement, if any error happens, it will exit immediately from it and it will return, right? This is the a basic structure from a select statement in Golang. And yeah, it's pretty straightforward. Okay, now let's test this in action. Let's return an error on the boil function, which is the fastest task. With that, we'll be able to check if it's gonna immediately return the error and exit from our select statement, right? So let's do that. As you can see, it only took 200 milliseconds, right? This is amazing. If we go back, you'll see that it will complete our tasks. Okay. Now let's see some more key concepts about low-level programming that will stand you out from the crowd. Let's see about processes versus threads. There are many more differences, but these are the main ones. Processes cannot share the same memory spaces, like code, variables, files, and so on. But different threads in the same process can. So this is a multi-threaded process, and this one is a single thread process, right? When you have multiple threads inside a single process, you can share a lot of things which other threads pretty easily, like code, variables, data, files, signalings, and so on, right? But you have things that are specific to thread, right? The number two is threads are lightweight. They are semi-process, a segment of a process, right? threads can easily communicate with each other. So the communication process in threads are much easier than with process, which are much more complex. Okay, now that you have a basic understanding of what a process is and how it differs from a thread, let's take a look at the differences from threads and goroutines. First and foremost, goroutines are not threads. They are lightweight threads, okay? That said, let's see some of the differences between them. The first one is size. As you can see, goroutines are much lighter than threads, right? They have only 1% of the size that an actual OS thread have. And there are a number of reasons for that. OS threads have to deal with a lot of operational system needs, and goroutines don't. Because goroutines are so small, you can spawn thousands of them without significant memory overhead. This allows us to manage insanely, blazingly fast systems without much hardware resources, okay? OS threads have a lot more size because they need to handle capabilities and protections that that are just provided by the operating system, such as the stack size, which which will handle function parameters, return addresses, local variables, and so on. Goroutines have much smaller stack size, and it can easily be increased if you need to. Okay? OS threads also have interrupt vectors that indicates when an event needs immediate attention, like when you press a button on your keyboard, which will require a specific attention to be done, a specific task to be done, and of course, much more. OS threads have much more things going on. The go run time will handle a lot of the hardware and CPU specific stuff that you need to. Okay. Another thing is hardware dependent. Go routines are not, and threads are. So OS threads must manage thread states, context switches, and interactions with hardware, making them dependent on the specific hardware and the OS itself. Okay. And Go routines, on the other hand, they're managed by the Go runtime. So the Go runtime will abstract the underlying hardware. So Go routines do not need to directly interact with the CPU or the operating system. And this abstraction allows the Go runtime to optimize the scheduling and the execution of Go routines without being constrained by hardware specifics. We also have the ease of communication. In Goroutines, you have channels. In threads, you have a much complex ways to communicate. Yeah, Goroutines you can communicate with other ways, but yeah, especially it will be especially with channels. Okay, primarily in OS threads, you have a much more complex system to communicate. Most of the time you have to use a lot of locks, mutexes, semaphores, or condition variables. You also will be managing shared memory, and synchronization can be really complex. The message passing on OS threads may include using IPC. Yes, you can use that, which is inter-process communication, and oftentimes it will involve the kernel, which will, yeah. You also have the creation speed. As the goroutines are much smaller, that they can be created much faster, right? You have context switching, and switching between goroutines is much quicker than switching between OS threads because the Goro time it minimizes the overhead when switching between tasks, which improves performance and when running multiple routines, right? OS threads, on the other hand, are much slower because the OS has to save and restore much more state information, and it must ensure fairness and security, which increase the time taken to switch between threads. So yeah, that's a lot of overhead. And we also have scheduling, right? And with Go routines are much easier than with threads. In Go, the runtime handles scheduling Go routines efficiently without the need for complex prioritization. It will make much more easier to manage concurrent tasks. OS threads, on the other hand, it uses a complex scheduling module, and the operating system needs it will manages thread prioritization and fairness across all running applications, which adds complexity and overhead. Trust, the lack of trust is really worth paying more attention to. So the Go runtime makes several assumptions on your software. It assumes that Go routines will behave well since they are part of the same program, which and this program is compiled by a trusted compiler. So the Go runtime avoid many of the safety checks and overhead for improving performance. So it doesn't have to worry about the bad behavior of a Go routine, because if Go routine, if one of these Go routines misbehaves, it's probably just a bug on your program, on your software, because algo routines are running on the same program, which are essentially which is essentially compiled by a trusted compiler, right? OS threads, on the other hand, can't have this luxury assumption. So they're untrusted. Were not compiled by a trusted compiler and may not have been compiled by the same compiler at all, right? So also threads could have been written by a malicious people trying to break or invade our system. For this reason, the OS must enforce strict rules and protections, which adds to the overhead and complexity. And yeah, that's it for today. I hope you have learned something useful, and let's revise some core concepts. So we have learned today about the difference between concurrency and parallelism, threads and processes, communication and waiting mechanisms in Go, select statements. Go routines are not threads, right? And we saw the differences between them. So if you found this video useful, share with someone and leave it a like. So that's it for today. I see you on the next video.